Hello everyone. Today we are going to analyze this cantilever beam. In this beam there is a concentrated load W. It acts at a distance of A from the fixed end. We know that in the fixed end A there will be a vertical reaction and a movement. Let us keep the vertical reaction as RA and the movement as MA. Let us apply this rule and find RA. RA is acting upwards so that it will be positive. W is acting downwards so it will be negative. For RA, we will get W. Now from the point B, let us take a moment about A and find MA. We have to follow left hand side rule. Clockwise will be negative and anti-clockwise will be positive. The load W is acting in the clockwise direction so that it will be negative and the distance is A. The moment MA will be acting in the anti-clockwise direction so that it will be positive. For MA, we will get WA. Now I'm going to find the shear force values from the point A and towards the point B. In this case, I have to follow right hand side rule. Upwards will be positive and downwards will be negative. Shear force at just left of A is 0. Shear force at just right of A is W. It is acting upwards, so it will be positive. At just left of C, we have only this reaction W. At just right of C, we have this and this. Since it is acting downwards, it will be negative. So for the shear force at just right of C, we will get 0. The shear force from the point C to the point B will be 0. Here you can see the shear force diagram. Now let us find the bending moment values. I am going to find them from the point B. In this case, we have to follow left hand side rule. Clockwise will be negative and anti-clockwise will be positive. We know that in the free end B, the moment will be 0. In the point C, we have the point load, but for this load there is no distance. In this case, the moment at C also will be 0. Let us find the moment at just right of A. We have only this point load. It is acting in the clockwise direction so that it will be negative and the distance is A. Minus W into A, it will be minus WA. Let us find the moment at just left of A. In addition to this, we have the moment WA. It is acting in the anti-clockwise direction, so it will be positive. When we add these two, we will get 0. We know that in the point C and B, the moments are 0. Right of A, it is WA, and left of A, it is 0. Using that, we can draw this diagram. Using this bending moment diagram, we can find the slope and deflection in the point C and the point B. To find the slope and deflection, we can use the moment area method. First, let us find the slope in the point C. The formula is area of the moment diagram upon EI. We know that it is a triangle. We know the area formula of a triangle, half into BH. Here the breadth is A and the height is WA. So this is the area. The area divided by EI, we will get the slope. Let us take the point B. Up to the point B, this is the only area. So the slope in the point C and the point B will be same. That is WA square upon 2EI. Now we are going to find the deflection in the point C. The formula is area x bar upon EI. X bar is the distance of center of gravity from the point C. The formula is 2 upon 3 into breadth. Here the breadth is A, so 2 upon 3 into A. The area we know, then we have to multiply with this distance. When we divide this by EI, we will get the deflection at C. which is WA cube upon 3EI. Now let us find the deflection in the point B. In this formula, area is same, but the distance of center of gravity will be different. We have to calculate the distance up to the point B. This distance is L minus A. So with this, we have to add L minus A. For these two terms, we can take LCM. We have to multiply with 3. In this way, for the deflection at B, we will get this expression. Alternatively, we can find the slope and deflection at any point of the beam using MACAULAY'S method. We have to make sections. In this beam, there are two different parts, AC and CB. So we have to make two sections. You can see that I have made two sections, one in AC and one in CB. Both of the sections I have made at a distance of x from the point A. Let us find the moment in the sections. From the point A, I am going to find the moments. In this case, we have to follow right hand side rule. Clockwise will be positive and anti-clockwise will be negative. The movement MA is acting in the anti-clockwise direction, so that it will be negative. The reaction W is acting in the clockwise direction, so that it will be positive, and the distance is x. So this section is over. Now we are going to consider this section. In between both of the sections, we have only this point load. This point load is acting in the anti-clockwise direction, so that it will be negative, and we have to take this distance. This distance is x minus a. These two terms should be separated by this line. Then we have to equate the movement to ei d square y upon dx square. Then we have to integrate on both of the sides. When we integrate this, we will get dy upon dx. We can integrate these two terms using this formula, and we can integrate this term using this formula. In this term, there is no x, so the integration will be x. When we integrate x, it will be x square upon 2. C1 is the constant. When we integrate this, we will get this. Again, we have to integrate this on both of the sides. When we integrate dy upon dx, it will be y. When we integrate x, we will get x square upon 2. When we integrate x square, it will be x cube upon 3. In this term, there is no x, so we have to multiply with the x. C2 is the new constant. When we integrate this, we will get x minus a the whole power 3 upon 3. 2 into 3, it will be 6. In the point A, there is a fixed support. In the fixed support, there will be no slope. Dy upon dx is the slope. In the point A, x is 0. So in this equation, we can apply 0 for x and for dy upon dx. When we do that, we should not consider this term. In this way, for C1, we will get 0. Also, in the fixed support, the deflection will be 0. So when x is 0, y will be 0. In this equation, we can apply both of them. We should not consider this term. In this way, for C2, we will get 0. In these two equations, we can apply the values of C1 and C2, so that we will get these two equations. Now let us take the slope equation. For x less than a, we should only take this. We should not consider this. Simplifying this, we will get this. When x is greater than a, we have to consider this term also. We can take w upon 2 outside. In this term, there is no 2, so we have to multiply with 2. For this, we can apply a minus b the whole square formula, that is a square minus 2ab plus b square. Using that, we will get this, but here there is negative sign, so we have to change the sign like this. We can eliminate x square and 2ax. So for dy upon dx, we will get this. You can notice that in this term, there is no x. That means in the beam, from the point C to the point B, the slope will be same. So in the point B and in the point C, the slope is minus WA square upon 2EI. To find the slope when x is less than a, we have to use this formula. Let us keep this as equation number 1. And when x is greater than a, this is the slope. Let us keep this equation as number 2. Now let us take the deflection equation. To find the deflection when x is less than a, we have to only take this. We should not consider this. We can take W outside. For these two terms, we can take LCM as 6. This is the equation to find the deflection when x is less than a. Let us keep this equation as number 3. When x is greater than a, we have to take this also. We can take W outside. Then we can take LCM. Let us keep 6 as LCM. Using a minus b the whole cube formula, we can expand this like this. Then we can eliminate these two. We can eliminate x cube. We will have only this. This is the equation we have to use when x is greater than a. Let us keep this as number 4. Now let us find the deflection in the point C. We can use any one of them. Instead of x, we have to apply a. Finally, we will get this formula. To find the slope in the point B, we have to take this. Instead of x, we have to apply L. We can take a square outside. Finally, we will get this formula. This is the elastic curve. Here you can see the summary of what we have done. Now we are going to end this session. Thank you for watching this video.